This morning, then, we'll continue our discussion about cardinal arithmetic. Last time we saw in the recorded lecture Hessenberg's theorem. That showed essentially there was a bijection between any infinite cardinal and the Cartesian product with itself. So kappa is bijective with kappa cross kappa. And from that, we deduced a couple of corollaries that showed that cardinal arithmetic was rather simple, given its definition. If you took two cardinal numbers, kappa and lambda, if you wanted to just add kappa to lambda, what you had, the result was just the larger of the two. And it was the same for multiplication. So kappa plus lambda is the same as kappa times lambda, and it's whichever's the larger. So today we'll consider cardinal exponentiation. This is altogether a completely different ballgame. And although the definition is simple enough, and we'll use a previous exercise to get some exponentiation laws going, actually in set theory, we hardly know anything about what the cardinal exponentiation function is like. It's consistent that it's kind of very simple and nicely defined, but it's also consistent with the axioms that it's kind of wild. And we have no fixed idea beyond some rather general results, general bounds of what cardinal exponentiation is like. But we'll go first towards the definition of it. So this will be, continuing in the notes, at definition 430. But before that, I'd like to just consider some lemmas about unions of countable sets. So this was the sheet on Hessenberg's theorem, which I'm not going through again now, just to focus on. So definition 428. So let A be any set. Then we define, it may look a slightly strange notation until you get used to it. This is less than omega into n. A to the b is supposed to be the set of functions with domain B in range in A, right? So actually here, what we're doing is just saying this is the union of functions from some finite n, natural number n into A. Right? So this is this here. So corollary 429 here. Suppose I've got an infinite cardinal. Right? So again, this is an ordinal, and it's its own cardinality. There's no bijection between this and anything smaller. So it says the size of this set of functions from finite numbers into kappa is kappa. So that is its cardinality here. We use here exercise 428. And it's a way of, we identify the functions, or we can think very easily the functions from n into kappa as just being n sequences from elements from A. Recall that this notation, a to the n up here, is shorthand for the n-fold Cartesian product of A with itself. So it's just a way of thinking. This is a function, right? This is a set of ordered entuples here. Of course, the function delivers for you an entuple, right? So actually the exercise is kind of easy. Right? So this guy over here is in here, whereas of course the function is over here. And of course, if I've got any ordered entuple, I can just think of it as a function. Right? First thing, second thing, up to the nth thing here. So the bijection you're supposed to provide in the exercise between this and this is given by just this here. So this is clearly a bijection. So I myself, I often slip up and say, oh, this is a function. Or I say something in here is an integral sequence, right? Okay. So back to the corollary that we've got to prove here. It's enough to show that if I let xn be the collection of functions, so this is df for definition. I define xn to be the collection of functions from n into kappa. I'll show that this has got cardinality kappa. So then we use another exercise. And what does exercise 429 do?
Sorry, can you move the page up, please?
Sure. So we assume the well-ordering principle. which we do usually anyway, but it's just emphasizing that it's necessary here. Suppose xn has cardinality kappa, where x kappa again is infinite. Show that the union of these xn has also got cardinality kappa. Okay, so let's assume this for the moment, and we'll come back to it. So how will this help here? Well, here we've got these xn's, right? If I can show xn has cardinality kappa, the union of the xn's here is the union of the things that I want, all of these sets of antiples from kappa here. The union of these xn's is this. So if each xn has cardinality kappa, the exercise shows what we want, right? Precisely what we want in the corollary here. So if each xn has size kappa, okay, but indeed this is the case, right? Since n to the kappa, this is xn, here, this is bijective with kappa to the n, right? This was exercise 428, which we just did. But Hessenberg's theorem says kappa cross kappa is bijective with kappa. And you apply that n times here. So by repeated application, we get all of this is bijective with kappa. So xn is bijective with kappa. Which is what we were trying to show here. We wanted to show each xn had got size kappa. So we've done that, and then we apply the exercise, and we then get the union of the xn's as size kappa. So that would finish the corollary. So let's just look at that exercise. Okay. So let me write it down again. Now, actually, the proof of this is very similar to the proof that a union of countably many countable sets is countable, which is just the case when kappa is omega. This was I don't know quite what number this was. This was lemma 418. So actually, we can just kind of copy that proof. And I'm not entirely sure why I put a little star against this. I said here star means a slightly harder exercise. I don't think 429 really deserves a star. Okay, I think there's no harm in doing this again. In fact, what we'll show is, so let's do something better. Suppose I've got x alpha, alpha is less than kappa, is not just a countable sequence in less than omega, I've actually got a kappa sequence or sets. And each alpha has got size kappa. Again, this is greater than omega. So I've not got just a x1, x2, x3, x4, and xn, and so on. I've got x alpha for every alpha less than kappa. We'll show that the union of all of these is kappa. So the exercise is a particular case where I only take an omega sequence of sets. But still, it's pretty much a copy of that previous proof. We just use the ideas of the previous proof. So again, the difficulty, if there is one, is because all we're told is that these sets of size kappa, we haven't actually been given the bijections between x alpha and kappa. So we've not been given the required bijections. We're just told they exist. That's all the information that we're given, right? Just says there is a bijection between this guy and this guy. So we have to choose them, we have to find them. And that was where the well-ordering principle came in. So taking the notation from before, now I'll let Z be the collection of possible bijections. Where G takes now kappa bijectively with X alpha. So if you look back and compare what we did then, we said there was an I less than omega, right, which took omega bijectively with Xi. So again, Z is a set. It's a subset of the union of all possible functions from kappa into X alpha. So I can justify that this is a set, this union is a set. By the axiom of subsets, this will pick out Z. But that's not the issue at the moment. We then well order Z using the well ordering principle. And this is the trick that allows us to pick out functions, to choose functions that we want. I can just look in the set Z, and I look along the well order until I find the thing I want. So this is a mechanism, this kind of linearizing, if you like, of Z, or well ordering of Z, is what allows us to go through the set Z and pick out what we want. So let G alpha be defined as the R least element of Z, which is a bijection of the kind we want. So we do this for each alpha less than kappa here. Now by Hessenberg, we've got a function that goes from kappa cross kappa bijectively with kappa. If you look back at the previous argument, we appealed to the existence of a function with omega cross omega bijectively with omega. So now we're stepping this up to kappa. So we'll now take a function, we'll define a function G from kappa to this union of all the sets that we're interested in here. And we do the same as we did before. What G will do, it will look at the alpha beta thing, it'll look at the ordinal, it'll assign to the ordinal that F assigns alpha and beta to. The beta thing in the enumeration of X alpha. So once one figures that out, then you see that so the domain of G is just the range of F, which is kappa. And you can now check that this is onto here. It's an onto function. So this, because it's onto, the cardinality of this is less than or equal to this here. But on the other hand, each of these has got size kappa. So there's certainly a one-to-one function from kappa into any one of these x alphas, and so into the union. So there's a function h, say, from kappa, one-to-one into the union. Hence, the cardinality of the union is also greater than or equal to kappa. So it's equal. And that's what we were trying to show up here. So as a slogan then, exercise 429 just said, show that a countable union of sets of size kappa has size kappa. But we've gone one better. We've shown that a collection of sets of size kappa, each of the sets of which is a size kappa, their union's got size kappa. Okay. Sorry, just answering a question there on the chat. Right. Okay. So that covers corollary 429 and the exercises just above it. So now comes the promised definition of cardinal exponentiation. So this is definition 430. Again, I put WP in here. It's kind of to emphasize that it depends upon the well-ordering principle. As I've said, we assume WP really throughout the course from the moment we introduced it. But some definitions are completely impossible without the well-ordering principle, and this is one of them. So I take two cardinal numbers, kappa and lambda. Now we define kappa to the lambda, to the power lambda. And in the spirit of how we defined additions and multiplications, we take sets of size kappa and lambda, and we look at the functions from the lambda-sized one to the kappa-sized one. And that collection, we'll say, has got cardinality kappa to the lambda. Where L and K are any sets cardinality of L is lambda and the cardinality of K is kappa. Right, so this is a collection of functions from L into K. So exercise 430 says, show that this definition doesn't depend upon the L and K you choose. So the point there is, if you take another pair, K prime, L prime, with the same cardinalities, this shouldn't be making any definition to any difference to the result. Right? And what you're also asked to deduce is the equations that follow are sort of formulating that idea as well. There's an exercise really in keeping a cool head as to what the various notations mean. So again, let's just look at the kind of thing that we're presented with. This is a set of functions from x into y, and that's its cardinality. This is the cardinality of that set y. So this is an ordinal number. So this is again a set of functions from x into that ordinal number. And now here x has been replaced again by its cardinal number. And now this is the collection of functions from this cardinal number into that. Right? And the definition we've just given is this last bit. So this is definition 430. So there are a number of ways of presenting this. So let's pick any sets. So this is the K and the L. So we know there is a bijection of x with lambda. Sorry, I've got them. Let's see. Sorry, I want y down at the bottom. So I better have these the other way around. Right, so this is going to be kappa to the lambda. So I've got a bijection of x with lambda and one of y with kappa here. So these are sets, kappa and lambda are cardinals. So I'll just define f, which takes functions from x into y, into functions from lambda into kappa, right? Which of course is lambda into kappa here. So what can I do here, right? I've got a function from x into y, right? And maybe it's some h here that's going from x into y. And I've got f that takes x bijectively with lambda. And I've got a g that does the same thing for y bijectively with kappa. And I'm supposed to have a function from lambda into kappa. So I've just got a little like commuting diagram here. And I just use the following. So I'll say that let f of h be the function that's the inverse of f followed by h followed by g. And then that will be a function from lambda into kappa over here. So that was f to the minus 1 followed by h followed by g. So it'll go around like this. So this is in lambda, sorry, kappa to the lambda here. Now, you can check that this is actually one-to-one. Basically, if I change this function h to some h prime, I've changed this. No, I mean, you should check, really. If h is different from h prime, then f of h does not equal f of h prime. I've changed this function here. So it's going to do two different things. It's going to do h and h prime are going to do two different things on something in their domain. Right? So that's going to change the function here. So I'll just let you check this. But f is also onto. Okay, so I'll take a function here, k, and this has to be big F of something. So let k be a function from lambda to kappa. And I'll just use the same diagram again. I'll work out what this h has to be. Right? K is f of h, Well, what do I want? I want a function from x to y, an h here that's going to go over to this k. Right? So I could just take x by f, something in x over by f to lambda. I apply k, and then I apply g to the minus 1. These are bijections, so there's no problem with domains and ranges. So I'll let h be the function I just described. First a, f, then k, then g to the minus 1. F, then k, then g to the minus 1. So we've got this bijection between these two. Hence, this here is the size of this. But as we've said, lambda is the size of x here, and kappa is the size of y. And I could also add on to this that as well. So our definition of cardinal exponentiation doesn't depend upon what L and K are. I just took any X and Y here with these sizes. And I showed that there was this map from collection of functions from X to Y into the functions from lambda into kappa, right? This bijection here. So this is what happens in general. If you find that two sets are bijective, right, then you can immediately write down something in terms of cardinalities right here. So we just transfer something like this to something like this, kind of after a while, almost without thinking about it. We did this during Hessenberg's theorem, or the corollaries to Hessenberg's theorem. We had a string of inequalities of sets that were injective into each other. So you know immediately that their cardinalities are less than or equal to each other. And we just write that down. Okay, the other identification that one wants to make is with power sets and characteristic functions. So this occurs in Lemma 431. We've got cardinals kappa and lambda. Lambda is infinite, and kappa is at least 2, could be finite, and it's less than or equal to lambda. Then collection of functions from lambda to lambda is bijective with the functions from lambda to kappa. It's potentially much smaller cardinal here. Could be 2, could be lambda, or anything in between. So we bring out the fact that kappa could be 2 here. And this is in a one-to-one correspondence with the power set of lambda. And this is what I was just saying. A stream of equivalences, bijective equivalences here, we just write down straight away what the cardinality is. Lambda to the lambda is kappa to the lambda is 2 to the lambda is the cardinality of this power set of lambda. Because this is the cardinality of that, and this is the cardinality of that. So this is just definition here. And because they're bijective, they're the same cardinals. Now, the twist at the end here is given by characteristic functions. For subsets of lambda. With those subsets. Themselves. That might sound just a little bit cryptic. So what do I mean here? If G is in from lambda to 2, then let AG be the alpha less than lambda such that G of alpha equals 1. So this then gives us a subset of lambda. And conversely, if I've got A in a subset of lambda, then let GA be the characteristic function in lambda 2 to the lambda, where G of A of alpha is 1, if and only if 1 is in A. Sorry, if alpha is in A. So this is what I mean by identifying a characteristic function with a subset here. So there are as many characteristic functions as there are subsets because of this bijection here. So we've got this string of things here to worry about. Well, functions from lambda to 2, they're just a subset of the functions from lambda to kappa, because kappa is greater than or equal to 2. So this injection in inverted commas from here to here, this in fact is just the identity, because this is a subset of this. And likewise, this is just a subset of this. Right? So again, the one-to-one function here, this is just the identity. Right? And now what is a function from lambda to lambda? It's a collection of ordered pairs. First thing from lambda, second thing from lambda. Right? So it's a subset of lambda cross lambda. So again, this is just the identity. This just is a subset of lambda cross lambda. And now we'll use the Hessenberg theorem that says that this set has got the same size as this set. There's a bijection between here and here. So there's a bijection between their power sets. So I'm using Hessenberg here. If two sets of the same cardinality, then their power sets are going to be bijective here. And this we were just discussing above is bijective with 2 to the lambda. So in fact, we've got here 2 to the lambda and here 2 to the lambda. So actually all of these things are going to have the same cardinality. And this bit, which I don't really need, here, and again, here, 2 to the lambda. So we'll see then, cardinal exponentiation very much depends upon the exponent, right, here. If you've got anything that's less than or equal to the exponent, right, it doesn't matter whether you write 2 to the lambda or lambda to the lambda. Right? So these have all got the same size. So next time, we'll go over the page and we'll look at some more rules for cardinal exponentiation. Okay, I'll see you then.